All right, let's get started with the weekly contest 396. We're going to be doing all 4 problems from scratch. Let's get started with Q1. Hi, Lucia. Welcome to the stream. Have you done this one? So this one is called valid word. A word is considered valid if it contains a minimum of 3 characters. It consists of digits 0 to 9 and the uppercase and lowercase English letters, not necessarily to have all of them. It includes at least one vowel, and it includes at least one consonant. Kind of laggy. Is that happening to anyone else? Return true if word is valid, otherwise return false. Okay, so yeah, so in this problem we just translate this into code. So maybe we can happen to me too, but now it seems fine. Okay. I wouldn't know what to do, I think, to fix it, so it's good that it's better now. Okay, so we have these conditions. Can I make this bigger or what? I don't know. So I like my drawing board, so we're gonna start here. Why not? So we have here we have the first one. So we have 1, 2, 3, and 4. So 1 is that the length of the word must be greater than or equal to 3. Then it should have either digits or uppercase or lowercase letters. So that in Python can be written. There are 2. So the character must be alpha. I think it's called is alpha, which means that it's an uppercase or a lowercase English letter. So is alpha. Or C is digit. Okay, and we want all of them to be either one or the other. So for C in word, we want all of this to be true. Then we have condition 3, which let's say we have the vowels here. And we want any in this case, and we want to map is vowel to the characters of word. And finally, the same thing but with is consonant. So let's copy that here. So we have the vowels, and we have is vowel or is consonant, which means that, oh, sorry, this should be lower, because we have only the lowercase vowels, and we want a consonant if it is not in B and C is alpha. Okay, and so we just have the conditions here. Let's shorten the name, why not? So the length, then we want all of them to be alpha or digit, and we want any to be a vowel, and here same thing with is consonant. And those are the conditions, and they pass the examples. So yeah, it's pretty much translating what we're told into code, right? And knowing our libraries, like all this is not. So sometimes I see people who kind of are reinventing the wheel, and they do some kind of nice use of helper functions. Yeah, thank you. So sometimes I see people that do some kind of some kind of operations with the ASCII values of the characters, and I think that makes no sense. Like, just use the library functions. Every language has this kind of functions, and or even, I don't know why people hardcode like the number, the ASCII value of I don't know, of the lowercase a, like 97 or 65, instead of just getting the is a lot more readable to use the actual character. Anyways, let's go to Q2. So minimum number of operations to make word k periodic. You're given a string word of size n and an integer k such that k divides n. So yeah, so k is a divisor of n. Interesting. In one operation, you can pick any two indices I and j that are divisible by k. Then replace the substring of length k starting at I with a substring of length k starting at j. That is, replace the substring with the substring, return the minimum number of operations required to make the word k periodic. And here we have the definition. It is k periodic if there is some string s of length k such that word can be obtained by concatenating s an arbitrary number of times. For example, here we have word, which is AB, 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 and then word is a 2 periodic for S. Yeah, 2 because this is size 2, I think. Yes. So you repeat AV 3 times and you get AB, 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 of course. And here, example 1, we have LeetCode lit, and the answer is 1 because we can set code. We can set code into any of the other two, leet, and then we have Then we have leet, which is a for periodic. And we made only one operation to get there. And here the output is 3 because, yeah, we don't have any pair, any consecutive pair that repeats. So that means that we have to change all of them except one, right? And so the length is 10 to the 5. Okay, so let's see. Is the problem clear? So, I mean, the operation might be, was a little formal, but essentially, so we're given a string. We're given a string and some number k that divides, let's say this is 4 and this is, and n is 16. A whiteboard refresher is always nice. Okay. So maybe here you have a v. So you have to break it down into. Oh, here we will have 4 groups of size 4 each, right? And we can pick one operation as we choose 2 of these 4 groups, and we assign, we set one of them into the other, okay? And we want to make them all equal. And so notice that we have to choose one of the values, and we want to set that into all of the others that don't have that value. And the observation here is that you obviously want to, the one that you want to set to all of them should be the most frequent one, because that's going to minimize the number that you have to change. All the other groups that don't have, that are not the same as the most frequent, then you have to change them. So for each of them, you're going to spend one operation, and that's going to minimize the number of operations. And so we can do this pretty straightforwardly by, so we want to know which one is the most frequent. Okay, so yeah. So we want to know which one is the most frequent. So for that, we can use a counter. So we want to go over all the groups of length k. So this is a way that you step over, you define the range from 0 up to n, but the step is k. So you jump k places every time, and then we can use a slice to get that substring, the substring of size k starting on every. Does this mean that the I and j of on the operation would always be? Yeah, they would always be multiples of k. Here's where you're. No, it's just specified in the statement here. You can pick any 2 indices, I and j, that are divisible by k. Yeah, it's not that. Yeah, I know what you mean. So yeah, the problem could be more complex if you didn't have that restriction. But no, here is just, you have blocks of size k. from the beginning, and those are the units that you are dealing with. So here we go over, we break it down into all these units and we count them. And so then the answer is going to be, so we want to know how many are not, don't have the most frequent. So there are n divided by k blocks or groups, and we subtract the ones that are the most frequent. So for that we can do the max of the values of the counter, and this should give us our answer. And it works. So pretty concise code with Python. As usual, the Python is kind of a cheat code sometimes. Let's go with question 3. Minimum length. Lol, cool. Yeah, minimum length of anagram concatenation. Yeah, I recommend if you're gonna choose a language to do LeetCode and interviews, I always suggest Python. I know that in competitive programming, C++ is the most popular by far, but for interviews, I think Python is it's better, and for LeetCode, where the usually the time limits are not as tight, and you also have a different time limit for Python, which makes it more not so demanding. Anyways, minimum length of anagram concatenation. You're given a string S, which is known to be a concatenation of anagrams of some string T. Return the minimum possible length of the string T. An anagram is formed by rearranging the letters of a string. For example, AAB, ABA, and BAA are anagrams of AAB. Okay, so yeah, the permutation of the letters. So yeah, the size of the string is up to 10 to the 5th, and yeah, so here, I mean, the realization, so for T to be a concatenation, to form S by concatenating itself, anagrams of itself many times, then the length of T must divide S, right? So if we knew the size of T, then we could check. So remember one of the first LeetCode problems, which was telling whether two strings were anagram. So that one you could solve by counting, adding to a counter each string and then comparing, checking if they're equal. So we can do that here. We can do that with the first block. Once we know the length, right, the length of T, we can compare the first block with the second block. We create a counter of each block, and we compare it with the first one, and so on, and that will tell us if effectively it is a concatenation of anagrams. But the question is, how do we know the length of T? And usually, sometimes the answer is we don't. We just try them all. We try all the divisors, and yeah, that might you might think that that is too slow because we have, so the check that I just described is order 2, so it will do 10 to the 5 operations. But then we multiply this with the number of divisors of n. Okay, so how much is this? Well, if you remember how we find the divisors of a number, you might remember that you can go up to the square root of the number to get the because if you think about it, so if you are considering the divisors of n, right? So notice that the divisors come in pairs. So if a is a divisor, then it means that when you multiply it by b, you get n, so for some integer. So both a and b are divisors, right? And without lots of generality, we can assume that a is less than or equal to b. And so a must be in this range, right? It must be in this range, because if a, which was the smaller of the divisors, was greater than the square root, then when you multiply it by b, you would get something bigger than n, which is a contradiction. So that's why we can go over all the a's in this range, and we get the corresponding b by just doing n divided by a. This was going to be our b. And so that way we can find all the divisors, and this algorithm give us this bound. So the number of divisors of n would be less than this, right? Because for each iteration we're adding a and b to the divisors, and we are doing the square root of n iterations. But it turns out that there's a better bound that it's used in competitive programming, and it's I think it's something like this. It's the cube root. So this is bounded by the cube root of n. And notice that this is already, even if it was the square root, then notice that this multiplication would be 10 to the 2.5, so it would be 10 to the 7.5, which is kind of within the bounds. I mean, it's borderline, depends on the problem. But once you get this bound, then in that case, it should definitely be fast enough. So we can do that. So what we're gonna do is we're gonna go over all the divisors from smallest to largest, so that if we find one, we're asked to return the minimum. So if we find one that works, we just return it. So let's imagine that we have a function that gives us the divisors of n. So now we have the target counter. It's going to be so we do something similar than we did before. We're going to break it down into pieces of size d. So this is the first piece. So we create a counter of it, and then we want to know if all of the other pieces, I'm using different names for the same thing. I use grouped, I use blocked, I use piece, but yeah, it's just segments. Now I introduce another word. so of size d. So here we want to go over, so yeah, let's say we have this, and first we start at d this time, and the step is d, and we want again to create a counter of s starting from I and ending at I plus d, and we want to check if it is equal to the target. And if they are all equal to the target, then we found a solution and we return it. And we are guaranteed, notice that we're guaranteed to find that we don't need to do anything else because, well, in the worst case, we're gonna, the n is a divisor of n, and n is trivially works as, can binary search be used for this problem? Binary search on what? I don't think you can for, because you don't know that it's not true that for a it's not monotone, right? So if it's true for a divisor, it doesn't mean that it's true for, if it's true for a divisor, it's not true that is true for the smaller divisors, right? If it were, then you could do binary search, but it's not, right? Because you could have like 2, 3 as divisors, but 2 doesn't divide 3. You would have to have a chain of divisors to do something like that. Anyway, so yeah, and here, so the function to get the divisors is, so you could have this in a template. So this comes up sometimes. So the way I do it, so I have the divide, I start with d and up to the square root, but not including the square root. I'm gonna deal with the square root after the loop. And what I do is, in order to avoid sorting, I have a head and a tail list where I'm gonna put, so in the head I append this divisor, because these divisors, the smaller divisors, are going to be in increasing order, but the b in our equation is going to go in decreasing order. So that's why we add it to the tail. And here we check for the square root, because we don't want to add it 2 times. Right? If we did it here, we would have to check to. I mean, it doesn't matter in this problem if we add it twice, but it could matter in other problems if we want to reuse this function. So here, in this case, we add d also as a divisor, and here we return head concatenated with the tail reversed, right? Because we added to the tail from the largest to the smallest. And so now we have our divisors, and this is the code. But remember, this you should have on a template. I mean, I'm very used to writing this code, so I don't usually copy paste it, but don't do what I do. I think it's better to just copy paste it in a contest. All right, so yeah, one issue that occurred with this problem is that some people misinterpreted. They they thought that you could, instead of breaking it down into contiguous segments, they thought you could scramble them. And they thought it was more like a counting problem, and using GCD. And it turned out that the system tests were too weak, and they made those solutions pass. So I think that's why they're gonna make they'll make this contest unrated. I think they will rejudge with the stronger system tests, and if there's a change of over 10% in the results, then they will make it unrated. Lol. Yeah, I mean, it wasn't funny for a lot of people. They were very upset. But yeah, I guess you could. So in my opinion, the word concatenation has a very specific meaning in programming. So to be honest, I don't know how to make this consistent with this other interpretation. How to make I think the statement is fine to me. I mean, they could be more complete and include definition. I guess that would be better. Or they could have examples showing that what's expected. Hey, Kamsa. Thank you for watching. But yeah, I don't know. Yeah, they clearly dropped the ball here with the system tests. I don't know how they could miss this. I mean, they had to be pretty weak to not break that other solution. So I don't know. All right, so let's move on to Q4. So Q4, I think not many people solved it. Less than 200 people solved this one, and there were a lot of wrong answers, a lot of failed attempts. But let's see if we can make it easy, even though it's a hard. Minimum cost to equalize array. You're given an integer array, nums, and two integers cost 1 and cost 2, and you're allowed to perform either of the following operations any number of times. Choose an index I from nums and increase nums of I by 1 for a cost of cost 1. Choose two different indices, I and j from nums, and increase nums I and nums j by 1 for a cost of cost 2. Return the minimum cost required to make all elements in the array equal. Since the answer may be very large, return it mod and the usual prime number. Let's write that down so that we don't forget. Okay. And here are the constraints. We get up to 10 to the 5th numbers. And the values are up to 10 to the 6th. Okay, so yeah, the first observation here is that, well, we want to use the second operation, the one that changes two indices, only if it's a discount, right? Only if it's a volume discount with respect to the cost 1. If I can do two cost 1s for the cost of the cost 2 operations, then I can just increase by 1 and I will do better. So we can start by checking that. Well, so if the cost 1 times 2 is less than or equal to cost 2, then we just want to return the cost by changing all of them, all of the operations. We're going to use cost 1, right? Because it's cheaper. And so how many do we have? Well, let's take the so we want to take all of them to the maximum, right? If we're going to do one operation, then we can get them all to the maximum, right? And that's going to be how many times we have to increment is going to be the maximum times n minus the sum, right? This is how many we have to increment by 1 to get them all to the maximum value. And we're going to do that by at cost 1. And notice that there's another, so the size can be 1 or 2. So notice that if the size is 1 or 2, then we also want to just we are forced to just do 1, right? Well, if it's 1, is obviously we cannot do the other operation. And if it's 2, when we increment both of them, we are not decreasing their difference, so we're not we're not making progress towards making them the same. So we can also say this, if it's less than or equal to 2, we also just will do cost 1. We're forced to do cost 1, right? So now let's think about the case where that doesn't happen, right? When we prefer to do cost 2 is cheaper than doing 2 of cost 1. So now we're in the case where cost 2 is cheaper than 2 of cost 1. Okay. Whoa. So that means that we want to do as many cost 2 operations as we can. So how do we do that? So notice that there's we don't know what's going to be the target value, right? The final value that they will all achieve. By the way, is the problem clear? Because maybe I'm starting to explain the solution without clarifying. Lucia, do you think the problem is clear? Okay. So here, so far, all good. So notice that we don't know what the target is. When we did only the cost 1 operation, then it was obvious that we wanted to take them all to the maximum, because there was no benefit to make them all larger than that. But when we're doing operations by 2, then there could be there could be a benefit in going over the maximum, right? So we don't know what that. So let's first start by saying, let's say that we know. Let's say that we know that this t is going to be our target value. That they will all be increased up to target. Okay. Then we're gonna have s, which is going to be the sum of the nums. We have n, which is the size, and so we want to do as many cost2 operations as we can. So we can think about it this way. We can do this this rectangle to represent the operations that we're going to do. Right? So the size of this is going to be the first operation, then this is going to be the second operation, the third operation, and so on, up to, and how many operations are we going to need? Well, like we saw before that, so we want all of them to reach t, right? So the total sum must be t times n at the end, and we want to subtract the sum, right? The values that they already have. So this is how many we have to increase. But there could be a parity issue, right? We have to divide this by 2 to get how many operations we can do at most of cost 2. This is going to be the total number of operations of cost 2 that we have to do. Well, that we want to do to minimize the cost, the total cost. Okay, so let's say we have here all the operations. So notice that we can assign, right? We can say, okay, we're gonna, so let's say that we need 3. We need to increase the first, so the first number by 3, right? So let's save this 3 for this number. So this is 0. This is 0, 0, and 0. Well, I think this is not. Yeah, I think this blue thing is going to help visualize this, but let me. So what does this mean? This means that we need to increase. So t minus nums of 0 is 3. It means that we need to increase it by 3, right? So let's reserve the first 3 operations for 0, for element 0. Then element 1. Element 1, let's say we have to increase it by 4. So we save this 4. Then so on, we keep going with 2 and so on. So we want to find out if we can do this, if we can do them all, right? And then when we get to here, to the end, we start from here, right? So let's say here we're at 5. So here we have 3 operations for 5. We have to increment 5 by 3. So we do 1, 2, and we continue here. 5, then 6. We need only 1. Then 7. We need this many. So notice that all these operations are valid because we don't have in each column we have different numbers, right? So that means that they are valid. If we had the same number, then that would be illegal, right? Because we would the operation needs to choose 2 different elements. And so what happens? So when do we have a problem? Let's say that we have the number of twos, the number of times that we need to increment 2, let's say that we have a lot of them, right? We have 2, 2, 2, 2. We have 2 here, all here, 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 and we get to here, right? And in that case, we have a problem. But that's only going to happen if there's a nums, if the maximum of nums, let's call it mx, if it's greater than this number, right? This number here. If it's greater than this number, then we have a problem because we cannot do them without having a collision, right? Without having to increment one of them, which makes sense, right? Notice, so if we have, so one way of seeing this is that, well, I don't know if this makes sense to you, but or we can think about it like this. So if we have one that is too big, that is bigger than all the others, all the others, then even if we always increment this one, so we choose this one with this one, then we choose one of this with another one, and so on. We're gonna cover all of them, and we're still going to have some remaining increments to do for the maximum. So that means that we cannot increment them by the cost2 operation. We're gonna be left with some operations that we have to do of cost1, right? And this happens in this case here. So we can translate this idea into code. Let's say that we have here, so this is one option, right? To do all cost1. Remember to mod it. And so, yeah, remember what I said here. I said we're assuming that we know what the target is, but we don't know what the target is. So maybe we can do a search for target. So the target must be at least the maximum, right? Because we can only increment the values. And so here we don't know which values we have to. So let's say we do this. But once we know the target, then we know that the maximum yes, I think here we want the minimum. So the maximum one is going to be the target, the one that needs the most increments, the target minus the minimum, right? This is the maximum number of increments that we're going to need to get to the target. And then the total number of increments, it's going to be target times n minus the sum, right? And so we want to know if we are in this example, in this case where we have one that dominates, that is bigger than the half of the total. So we want to know if 2 times the maximum is greater than the total. Yes, if this is the case, then we have to do subtract this. We subtract the total because we're gonna pair as many elements as we can to the maximum, right? But then we're gonna have an excess because this one is too big. And so whatever the excess is, we're gonna have to increment them with cost 1 operation. And here the total minus the maximum, it's going to be of cost 2, right? So this is this case. Now in the other case we're going to do all the operations of cost 2 except if we have a parity issue, right? So the total, we divide the total by 2 and we multiply that cost. And yeah, notice that here this is this way. And then if we have a remainder, we're forced to do that one because the number of if the number of increments is odd, then we are forced to do one on its own of cost 1. So these are the 2 cases. Yeah, this is not returned. This is so here we want the minimum of this, or the minimum of this, right? So now we have to work out this part here. And so notice that once we get to this case, so when we increment the target, we are making, since the number of elements is greater than 2, when we increment the target, we are incrementing the total more than we are incrementing the maximum, right? So this, on this in this inequality, the total, when we increment the target, the total is getting bigger than the maximum, right? So eventually the total is going to exceed 2 times the maximum, so or half of the total. It's going to exceed the maximum, and we're going to be down in this case. And notice that once we are in that case, it doesn't make sense to keep incrementing the target, right? Because we're already doing all the operations that we can of pairs of cost 2, except for this detail, right? The detail of the parity. So okay, so let's see how we can figure out when the target will be big enough so that we got to the second example, right? So the condition that we have here is that we want 2 times the maximum or Yes, we want to do this in terms of the total. In terms of the, so we want to know what the target will be. So we want to fill in this blank here. So what we want is to know 2 times the target minus the minimum has to be less than the total. Well, but we also have to break down the total. So the total is the target times n minus the sum. So the target times n minus the sum. Okay? So we want to solve this inequality for t. Okay, so here we have 2t, well, so we move the t's here, so we have that t is n and minus 2, and then we have s, we move the s over here, and we have this, right? So now we divide by this. So now we know that if the target is greater than this number, then we're gonna be in the case where we can use all the cost2 operations. So notice, why do we care about this? Because it could be that cost1 is infinite. Well, I mean, technically it cannot be infinite, but it could be very, very large. And so it could be the case that you want to avoid doing even one of cost1. You want to do 0. And that's why you want to get to this case, right? And so we're going to get to that case when s minus 2 times the minimum. So here, so the sum minus 2 times the minimum divided by n minus 2, this is our final inequality, but it has to be greater than this, so we add 1 to it. And notice that we also have to be greater than max, of course, so we want the maximum between, the minimum between max and this. But there's a catch here. We might want to consider 2 consecutive values on this case, so that we change the parity and we avoid paying the cost 1 even one time. So that means that here we have to add 2 to it. And this is a very tight bound, I think. And remember that we have to mod here. Oh, here we don't have the max, so we can do this. And oh, yeah, I guess we have a problem here. Well, let's call this the all max. Well, this is not really the max. I mean, it's the max of the differences, so that's confusing, but okay. And whoa, wrong answer. Let me check. I got a bit lost. Could you do a recap? Yes. Can you tell me how, where, more or less, you got lost? So first I explained why. So I explained how we can find the minimum cost once we know what the target value is. Given the target value, how we could get the minimum cost. And the idea was that we had two cases. The for loop plus the if. Yeah, this part here. So this is what I explained. Oh, I think I deleted it. So remember when I said that we could pack the operations in a rectangle, and we only have a problem. So to see if we can do all the operations. So we are in the case here. We eliminated the case where it was better to just do cost 1. So we're now in the world where cost 2 is cheaper. And so we try to do all the cost 2 operations that we can. And we realize that we would have a problem if the number that requires the maximum increments was too big, was too dominant. It was bigger than half of the total, right? Which is this condition here. The maximum number of increments of a value is greater than half the total. In that case, we have to do the remaining operations individually, right? With cost 1. Whatever is so we always pair this one that is so big that we cannot cover it with two operations. We use it, we pair it with all the others, right? We increment this one, the maximum, we increment it, and we increment another one. Then we again increment the maximum, and we increment another one, and so on. But since the maximum is so big, then we're gonna run out of pairs for it, and we're gonna be left with only that value. So we cannot do more double increments. So for that excess, we do cost 1 operations. For all the others, we do cost 2 operations. Right? And if it's not the case, then we can do them all of cost 2, except if we have an odd number. If we have an odd numbers, then we are forced to do one single increment of cost 1, right? So this is how we solve the problem if we know the target. But then I said, okay, we don't know what the target should be. What's the best target? So let's just try values from the maximum and incrementing. Why do you have min in your for loop? Oh yeah, I think you're right. This is my bug. Yeah, just distracted. Now, let me see if it fixes it. Yeah, thank you. Drinking monkey. Thank you very much. So Lucia, did you? So I'm recapping. So then I said, okay, let's search for the target. Let's try a bunch of values for target until we find. But when do we stop, right? So we start at the maximum and we increment. But when do we stop? And what I said is that once we get to this formula right here, then it doesn't make sense to keep increasing the target, right? Because here we're already using all the cost2, which are the cheaper operations, all the cost2 operations that we can. The only exception, we might want to do 2 of this, because for the parity reason, maybe we can avoid by doing 2 of them. So maybe the total changes to an even number, and then we don't have to pay cost 1, not even once. And that's why I have this 2 here. Because once I get here, I want to do 2 times that. And yeah, that's the whole idea. So notice that this idea of doing the operations, and that's something that comes up a lot in CP. So it's good to know. And this idea of thinking as a rectangle that you're covering, I find it useful for thinking about this. So yes, this is all I got. So should the else statement technically run once? Well, twice. But yeah, I see your point. Yeah. I guess we could structure this on a different way. We could structure this on a different way with a for loop, and then doing this, I guess. I felt it was easier to do this way. But yes, you could definitely stop before this condition is false, and then let me think. Yeah, I guess another way. So I did it this way. I like to solve the inequalities, but I guess you don't need to. So we could do this. I don't know though. Yeah, no, you're exactly right, I think. So I guess a different way, without thinking, without doing the math, you could just say, okay, let's start with the target from the all max, and let's do this while well, yeah, let's say this. Let's get rid of this. And then we have the max and the total. And if this is not true, we break. Or yeah, I guess it's a little bit messier. I don't know. So if this is the case, we break. And then in the end, yeah, the thing that is a little messy is that we are going to have we have to loop through this. We have to do it twice. Well, maybe we can just so what was this? This was total divided by 2 times cost 2 plus total mod mod 2 times cost 1. But then we want to increment total by n, right? Because we're incrementing, if we're incremented target by 1, so I guess this should work too, but I like the other structure a little bit more. Oh, but we're not, I forgot to increment so this is going to this is an infinite loop. Yeah, this is a different way of doing it without figuring out the this inequality. Yeah, the for loop is cleaner. I just remember you saying that at a certain point, adding cost 2 operations can only make the result bigger. Yes, yes, increasing the target once we are doing all the cost 2 operations, it is increasing it more than this 2 times won't help. It would be counterproductive. So yeah, thanks for the insight. Okay, let's see if we can rate someone. Is there anyone doing LeetCode? In roses. Thank you for the explanation. Thank you for watching. Same, thanks. All clear. Great. Yeah, this one, I think if you understand it, you should be proud, because it's not it was a hard one. I mean, only less than 200 people solved it. And like I mentioned, like I said, it's something that comes up in competitive programming, so it's useful to know. Anyway, so let's rate in roses. And yeah, thank you very much for watching.
TV, right? 7 TV, okay. So wait, let's find then.